Okay, so in this video, we're going to be primarily looking at time series data, and we're going to be looking at some graphs, line graphs, lag plots, ACF and PACF graphs. We're also going to build some autoregression models and do some differencing. So common analyses, basic analyses for working with time series data. So we're going to start by importing pandas and NumPy. And I have two data sets that we're going to be working with. We have some crime data and we have some transaction data. And we're going to be comparing how they're both time-based data, but one of them is going to be a little bit better for typical time series type analysis than is the other one. And so we want to be able to look at both of those. So the crime data, and we're going to import the transaction data, and then the crime data itself. This is the year is our first column. We've got population values, violent numbers of violent crimes, murders, all kinds of terrible things that happened. And the counts generally are not great to work with because, of course, as the population goes up, even if crime stayed stable as a percentage of the population, as the population increases, you could expect that the number of events would also go up. And even if crime rates were to go down, if the population goes up, again, the counts could conceivably also go up depending on how much difference that rate was. So one of the things that we're going to be doing is modifying our data so that we can actually compare it in a reasonable way. And we're going to see why that might be necessary from looking at some graphs. And then if we look at the transaction data, here we have, again, some date-time data. No times were included. These are just dates. And so we have date information, but we don't particularly have, this data is not necessarily recognized by the date time code itself as being thoroughly sequential. So we have a lot of things happening on this particular date, and we don't have the time information to fully distinguish that sequence. And you might expect that on any given day that, well, there might be sequences across days, that you might not have individual transactions be sort of related to each other in the way time series data typically is. And so again, we're going to see some differences in these kinds of data. Just because you have information about a date doesn't necessarily mean that it's good time series data. Anyway, we have a number of variables here in our data set. Not as many numbers. Now, if we look at the types, the year has come in as an integer. So it's not recognizing it as a time information necessarily, just another variable. All of the other information came in as integers, which is sensible. In the transactions, the transaction number came in as an integer. The purchase date actually came in as an object, which is a string. You see other objects in here. So pandas did not actually read this as a date time object. So again, that's sort of worth being aware of. Again, pandas is pretty smart. Often it can bring those in, but it did not, in fact, bring these in as date times. It brought it in as strings, which can happen. And this is why in previous video we talked about ways of modifying our date times, extracting date time information from string text. And so if you need to actually use a data set like this where the date times come in as strings, it's worth revisiting that previous video and think about ways that you can convert this column of value of string values back into date times. Now we're going to bring in some plotting functions here so that we can look at our data. So we're going to bring in matplotlib, we're going to bring in Seaborn, and we're also going to bring in some packages from stats models for doing autoregression and our ACF and PACF graphs. Now, the first thing that we're going to do is we are just going to create a very simple graph of our crime data. Now, if you just plot the whole data set like this, it's going to plot all of the variables on the same graph. And you can see that you run into a couple of different issues when you do this. So first of all, the year is plotted as its own variable, which is weird. The legend is so large that it basically takes up the entire graph. And the population, you can see the population is clearly increasing, and it is much larger than all of the other values at the bottom of the graph. And so this is not a great display of the data in this data set, but sometimes you just need sort of an initial peek at the data, and visualizing it is sometimes more useful than just looking at the raw numbers. And so this is going to confirm a couple of things for us. For instance, that maybe we don't want to plot the population on the same set of values as all of our other crime statistics. We probably also don't want to plot the year as the vertical axis. We want to plot it as the horizontal axis. And probably calculating rates relative to the population, since the population is climbing during this period. That would probably also be a useful transformation of this data. We can also modify the style, and we've talked about this in previous videos. In another video, we used white grid. Here we're going to convert to dark grid, and we're going to change the figure size to be 16 by 6. Now this is these properties are now going to apply to all future graphs. And so if I replot my crime data, so I have the darker background, I now have the grid on it. And because the graph is set to be larger, my legend is now not quite overlapping the entire graph. All right, now we're going to create a copy of my crime data, and I am going to, again, make these rate calculations. So I'm going to take my violent crime rate, and I'm going to take my violent crime total and divide it by the total population. Again, ideally, you would want to do this for all of the variables in your data set. We're just going to worry about one of them, and then plot the result in a subsequent graph. We're going to use the year variable and the violent crime rate variable in our plot. So in this case, we're plotting the violent crime rate. Again, this horizontal axis, ideally, we would like it to be years. We'll worry about that at another point. But years since 1960, since 1960 is the first year of our data. And you can see when you convert this to a crime rate, as you adjust for population, there was an increase in crime that maybe at least in part corresponded with the population, but also was independent of the population. And then at some point in the early 90s, the crime rate started going down. So again, the rates are actually more relevant when we're dealing with different population sizes than we are when it's just the counts. The counts are not very useful, generally speaking. Now, if we look at the transaction data, we have a whole different kind of problem. Customer ID all over the place. That's not, again, real data. We have the transaction number is continually increasing, and all of our other variables, the number of children, the number of units sold, and the revenue, they're all tiny way down here. Again, not a very useful graph. Notice all the categorical variables simply were not plotted when we did this. So we have some things that we need to extract from this. Again, not a useful graph, but it does tell us a little bit about some of the variables. These are very small. The transaction ID and the customer ID both need to come out of our analysis. Now here we're just going to plot revenue. And now that we remember, revenue is like way down here in one of these purple lines at the bottom. And when you pull out all of the other variables and you just plot revenue, this is also not very sequential. This looks very different than our crime data, which is clearly meant to be a sequential process. Here, it's just random and all over the place. We have things happening on each day that are, they're all random, maybe relative to the day. Possibly we could do some aggregating and we could average by date and then see if we could get some kind of a more sequential graph. But again, this is basically noise from what I can tell looking at this data. And there's a lot of observations. There's 14,000 observations, and there's just no trend or sequential pattern as there is with the crime data. Now we're going to try and look at the data set again, and I'm going to remove the transaction and customer IDs, and then we can then try to create some additional analyses. Now, in this case, what we're going to do is the next thing, we're going to do a lag plot. And what a lag plot does is if you have sequential data, it's going to plot the correlations between consecutive values in your data set. So one of the issues with time series data is that today's value is related to yesterday's value by some, events that occur sequentially don't just happen randomly typically. It's not like flipping a coin. The price of the stock market today is not going to suddenly be $10,000 less tomorrow and then $5,000 high, 5,000 points higher. Today's value and yesterday's value are going to both be very similar values. And there may be some movement one way or the other, but they're not going to be completely random, able to be anywhere in the total sequence of values at any point in time. And when there is no relationship, then you get a graph that looks basically like this, where the relationship between an observation and its preceding observation is actually not particularly well correlated. So this is suggesting that if you have a value and you have it and you relate it to its value one step further in time, and then you plot all of those comparisons like a correlation plot, that you don't really get a very strong correlation here. This is not highly correlated data. And so that suggests that there is no sort of trend or sequential relationship in our values in the data set. Again, maybe if we averaged the days, the daily transactions, maybe we would get a trend then. But the individual transactions on the days are not correlated with each other. If you do a similar graph for the crime rate, you get a very clear linear relationship that suggests that this year's crime rate and last year's crime rate are closely related to each other. Even if they're going up or going down, the values are going to be very similar. The speed of the change is not very strong. It's not random, as we saw with the transaction data. There is actually a relationship. Now, it's this second kind of crime data relationship with this clear linear relationship between consecutive values that allows us to construct autocorrelations and model time series data based on yesterday's value to help us predict tomorrow's value. So an autocorrelation plot is a special type of graph. It looks a little different in pandas than it does in some other functions. But the idea basically is you want to plot consecutive observations and calculate the correlation between values that have one time step between them, two time steps between them, three time steps between them, and so forth, and see how they're related to each other. And the number of lags, is the number of time steps between them, is listed on the bottom here. These boundary lines that are on the graph are basically giving you significance levels, and zero correlation means there's no relationship. So at about 15 years out, we are saying there's basically no relationship between the crime rate here and the crime rate over there. And the longer time goes on, you can see there is, in fact, again, very close to no relationship. In the beginning, there is some correlation between maybe, not only when there's no time step, they're completely correlated with each other, but they're very highly correlated at one time step and all the way up to, I would say, at least 6 or 7 time steps. There is a relationship between the outcomes. There is sort of an inverse relationship maybe out here, but when you're building autocorrelation models, you would, if you were to include this information out here, you would generally want to include all of the time steps, not just ones that are out here. And so when you're building an autocorrelation model, you generally only go until you fall below the significance level, and you don't use other ones that might pop up later. Other kinds of programs will plot these as bars rather than a smooth curve, but basically you get the same idea. If you're above the significance level, then these are lags, these are autocorrelated values that should be included in your autocorrelation model, presumably. Again, you generally want to test this. Sometimes the ACF graph, the autocorrelation plot, is sometimes best used to determine how a moving average would help you predict the model, and a partial autocorrelation plot is used for the actual autocorrelation. One of them takes into account previous autocorrelations, and so you don't generally get the run quite as long in a PACF. In fact, here what we're going to do is we're going to actually calculate for the revenue and for the violent crime data the actual correlation between between one observation and the next. And this one suggests that there is in fact no relationship. If you shift by 50 values, there's no relationship in the revenue data. We could shift by 1 value, and we also have a basically zero correlation in our transactions in our revenue data. If we look at the violent crime rate data, we have a highly negative correlation. If we do just one of them, we have a highly positive correlation. So that negative correlation is what's showing up here. Now, we can import the autoregression model from the stats models package, and we're going to do an autoregression model. We're going to take 2 lags in order to fit our model. And then, again, we're going to use, if we want to use the training test data split, we don't do randomization for time series data. Instead, we would set up the first 80% of the data and then take the final 20% of the data so that they remain sequential rather than fully randomized. I'm not going to worry about that in this example, but that is how you would do a test training split if you wanted to do some validation for your data. Okay, so we run this. The model parameters are going to tell us that there is a constant, which is pretty small, but then one lag back you would multiply the crime rate by 1.57, and then 2 lags back, you would reduce that by negative 0.6 in order to predict crime rate from one step to the next. So if I were to predict, let's say I had 2013 and 2014 data and I wanted to pick 2015 data, then I would use 2013 data here, 2014 data here, and then add this constant, and that would indicate what I would predict for the 2015 crime rate. Now, the PACF graph, I'm going to pull out of the stats models package rather than pandas. And we're going to plot only out to 20 lags in this case, again, comparing the violent crime rate data. And we're going to label it with partial autocorrelation. And we got a warning, which we're going to ignore. And again, this is the way autocorrelation graphs and partial autocorrelation graphs tend to look. You still have this thing in the center that's indicating significance. We do have potentially one sort of long-term significant value way out here. Obviously, when there are 0 lags, you get exactly perfect autocorrelation. But then we see that there 1 step out, there is very high correlation. 2 steps out, we see this negative correlation, and that corresponded to our coefficients. So a positive coefficient for the lag 1 and a negative coefficient for lag 2 that matches that negative autocorrelation. And again, in the regular autocorrelation, they are not accounting for how, let's say, lag 2 is influenced by lag 1. It's just looking at how lag 2 directly affects the current value. In the partial autocorrelation, they are removing the relationship between lag 2 and lag 1 in order to calculate the impact of lag 2. Now, another operation that we can do from the stats models package is we can calculate the p-value of our model. Now, the p-value, essentially here, what we're going to calculate is our data stationary or not? Is it random or not random? And so sometimes for autocorrelation models or other kinds of time series models, we're interested in knowing whether or not the data is random, whether it's stationary. And so this is actually a hypothesis test that says, yes, it's stationary, or yes, no, it's not stationary. Yes, it is stationary. In this case, the high p-value indicates that our data is in fact not stationary. Typically, if you want to analyze data and find out how many differences you need to take, how many relationships do you have to account for in order to get to stationary time series data, we do this by calculating the differences. And we will do this until the resulting calculations, the resulting differences are stationary, that we do get that stationary result. So essentially, we're taking the difference between observation 1 and observation 2, and then the difference between observation 2 and observation 3. So is that rate of increase stationary or not? And when we do one set of differences, we do in fact get a p-value that drops below. So that indicates that while the original data was not stationary, the differences are. So again, there's different kinds of time series models. Sometimes you need to know how many differences you need to take in order to get to stationary. Sometimes you need to know the full ACF correlation for moving averages. Sometimes you need to know the partial ACF for autocorrelation models. And so these different types of analyses give you different pieces of information that you can use in order to model the trend in your data. Now, again, I'm going to do an autoregression model on the differences that I just calculated. And if I fit my parameters, again, this is a 2-variable model again, but after calculating the differences, my constant is much smaller. It should be closer to 0. And my coefficients are also smaller. So they are contributing less to the changes. And that's what we would expect. Now, we would have to do, in order to really determine what kind of combinations of autoregression and moving average and other kinds of properties for our time series models, we would want to do further analyses. We would want to look at some metrics and things like that to determine which ones were the best fit in producing the best errors. We would want to do cross-validation with our test and training sets and things like that, which we're not doing here. Again, this is simply meant to be sort of an introduction to some of the tools that you can use when you are building time series models to kind of get you started with the analysis and a place to start looking for additional information and analysis.